Now, today we are going to start with the damped oscillations. What are damped oscillations? These oscillations is a type of a motion executed by a body subjected to a combined action of both restoring and resistive forces, and motion always gets terminated with the body coming to rest at equilibrium position in a finite interval of time. We have seen the equation of motion in simple harmonic motion where it is acted upon by only the restoring force. Now, damped oscillations, these are a type of oscillations where it is a combined action of restoring and resistive forces. That means along with the restoring force there exists a resistive forces due to which a mechanical oscillations of the pendulum comes to rest after a certain period of time. So such type of oscillations are called as a damped oscillations, where the oscillations comes to rest after a certain period of time. As said example, mechanical oscillations of a pendulum are nothing but a damped oscillations, that is they come to rest. Oscillations comes to rest after certain period of time, that is because of a resistive forces. Another example is a swing left free to oscillate after being pushed once. It comes to rest after few seconds, that is after finite interval of time these oscillations are coming to rest. Why these oscillations are coming to rest? These are nothing but a resistive forces. Air resistance is imposed on the motion which causes the motion to come to rest. Such oscillations are called as a damped oscillations. A simple oscillation, whatever you say, a simple pendulum is set into displacement. It oscillates for a certain period of time, and after certain period of time slowly the amplitude decreases and comes to rest, which is nothing but because of a resistive forces. Theory of damped oscillations. Now we are going to derive an equation of motion for the damped vibrations or the damped oscillations. Consider a body of mass m executing vibrations in a resistive medium. Let us suppose that air. We are going to find the equation or the theory of damped oscillations in air where there exists a resistance. So it is a resistive medium. Vibrations are damped due to resistance in a medium. That means they are getting damped, they are getting stopped because of a resistance in the medium. So resistive force is defined as, resistive force is proportional to velocity. Here you can see dx by dt. We know that dx by dt is nothing but rate of change of displacement, that is nothing but a velocity. So resistive force is proportional to the velocity, and removing the constant of removing the proportionality symbol, you are getting R as a damping constant. Here the negative sign indicates the direction opposite to the movement. So resistive force is given as minus R into dx by dt. Dx by dt is a velocity and R is called as a damping constant. Negative sign indicates the direction opposite to the movement. Another part of a force that is constantly acting on a body is nothing but a restoring force. So vibrating body is constantly acted upon by a restoring force. So restoring force is equal to minus kx, which we have already discussed. Now combined action of these two, the net resultant force is of two forces from equation 1 and 2. The resultant force, both the forces, that is the resistive force and the restoring force, have a negative sign. So the resultant force is minus R into dx by dt and minus kx. So this becomes a equation 3. From Newton's second law, the resultant force, that is F is equal to ma. It can be written as m into d square x by dt square. This is the equation 4. From 3 and 4, equation 3 has a negative sign, and the resultant 4, equation 4, F is equal to ma. So from equation 3 and 4, m into d square x by dt square is equal to minus R into dx by dt minus kx. That means left hand side is the resultant force and the right hand side of the equation is the resultant force, which is having a negative sign or the negative displacement. So rearranging the terms, m into d square x by dt square plus R into dx by dt plus kx equals to 0. This is the equation of motion for the damped oscillations or the damped vibrations. Solving the equation d square x by dt square plus r by m into dx by dt plus k by m into x equals to 0. This is the sixth equation, which we have rearranged the terms of the equation of motion for damped vibrations. So here this is a quadratic equation. Let us assume r by m is equal to 2b, and we already proved that k by m is equal to omega square. Substituting these two values, we are getting as d square x by dt square plus 2b into dx by dt plus omega square x equals to 0. That means substituting the value of r by m as 2b and omega square is equal to k by m, we are getting a second order differential equation as equation 7. Let the solution for equation 7 be x is equal to a into e to the power of alpha t. Differentiating this equation with respect to time, dx by dt is equal to a into e to the power of alpha t. Differentiating again, you are getting d square x by dt square is equal to a alpha square e to the power of alpha t. So here we have equation 8, equation 9 and equation 10. Substituting the values of equation 8, 9 and 10 in equation 7, you are getting another equation a into e to the power of alpha into alpha square plus 2 alpha b plus omega square equals to 0. This is a second order differential equation. Now from equation 8, we can say that x is equal to a into e to the power of alpha t. Taking that value as x, and alpha square plus 2 alpha b plus omega square equals to 0. Since here x equals to 0 corresponds to trivial solution, one has to consider alpha square plus 2 alpha b plus omega square is equal to 0. This is named as equation 11. The solution for the above equation is given by alpha equals to minus b plus or minus root of b square minus omega square. It is nothing but a solution for the second order differential quadratic equation, because alpha square plus 2 alpha b plus omega square is a quadratic equation. Substituting for alpha in equation 8, we get the solution as x is equal to c in e to the power of minus b plus root of b square minus omega square into t plus d into e to the power of minus b minus root of b square minus omega square into t. Here first term is having a minus b plus root of b square minus omega square, and the second term is having minus b minus root of b square minus omega square, where c and d are the constants. So this is the equation with c and d are constants. Now we see the three cases: overdamped or deadbeat. That is the case of b square is greater than omega square. When b square is greater than omega square, it is called as a overdamping or a deadbeat. Now if we take b square minus omega square is a positive quantity, since b square is greater than omega square, b square minus omega square becomes a positive quantity, which leads to root of b square minus omega square is less than b. Now the solution, whatever we have taken solution of x as c into e to the power of minus b plus root of b square minus omega square into t plus d into e to the power of minus b minus root of b square minus omega square into t. This is equation 13. If you assume that b square minus omega square is a positive quantity, then what happens? The coefficients of t in both the terms are negative. This indicates there is an exponential decay of displacement with respect to time. The body, after passing through its maximum displacement, comes to rest, called as overdamped or a deadbeat. So what is defined as overdamping is a condition where restoring and resistive forces acting on a body to hold the body at equilibrium position without an oscillation. So this is called as a overdamping case, and you can see the diagram here. See here the case of overdamping. There is an exponential decay in the diagram, the graph, where the graph is drawn between the displacement and a time. You can see the upper part where b square is greater than omega square, that is nothing but a overdamping case. Now second case is here critical damping, that is b square is equal to omega square. When you take it as b square is equal to omega square, this is called as a critical damping, and the equation 13 can become x is equal to c into e to the power of minus bt plus d into e to the power of minus bt. Here, if you look at it, x decreases throughout with increase of t. It decreases slowly in the beginning and then rapidly approach to 0. That means body attains equilibrium position called as a critical damping. You can see the graph here, it is critical damping, how it is coming to rest. Now how we define critical damping is, it is a condition under which restoring and resistive forces acting on a body to halt a body at equilibrium position without oscillations in a minimum time. So you can see the difference between over damping and the critical damping from the diagram there. Next, the third case is under damping case, where b square is less than omega square. When b square is less than omega square, b square minus omega square becomes negative quantity, and root of b square minus omega square becomes a complex number that we can take it as I into root of omega square minus b square, and the solution is given as shown in the equation. So if you see the diagram here, displacement between that graph between displacement and time, the amplitude gradually decreases and finally reaches to 0. As time increases, e to the power of minus bt decreases, so amplitude a into e to the power of minus bt decreases progressively, resulting in damping of vibration. So here in this case, the amplitude slowly decreases and finally reaches to 0. So we have seen the three cases where b square is greater than omega square is called as over damping, b square is equal to omega square is called as a critical damping, and b square is less than omega square is called as a under damping cases. So what is a under damping what is under damping is? Under damping is a condition under which restoring and resistive forces acting on a body such that the body vibrated with decreasing amplitude as the time progresses and ultimately comes to halt at equilibrium position, and this case is called as an under damping case. With the help of this, we define a quality factor Q. Q describes the amount of damping. Q is defined as a number of cycles required for energy to fall off by a factor of 535, that is approximately equal to e to the power of 2 pi. The larger number of cycles gives larger value of Q, means sustenance of oscillations is more in overcoming the resistive forces. Q is given by omega by 2b, which is nothing but equation of the quality factor. So larger value of Q means sustenance of oscillations is more overcome the resistive forces. So Q is equal to W omega by 2b, gives the equation of a quality factor. Thank you.